Good afternoon, sir, and everyone present here. Today, I am Arohi Agrawal with my fellow teammates going to present on the topic process synchronization. Today, I will be discussing a vital concept in modern computing synchronization. Whether it's a multi-core processor handling millions of tasks or a network of distributed system working together. Synchronization ensure that everything functions harmoniously. My presentation will cover how synchronization works in real-time system, high performance computing, distributed networks, and hybrid simulation platforms. I will also touch on the challenges this system faces and the innovative solution that have been developed to overcome them. Now let's start by looking at real-time system where tasks needed to be completed within strict time constraint like automotive systems, medical devices, or industrial automation. In this system, synchronization ensures that critical tasks such as sensor data processing and actuator control are carried out on time. Take the anti-lock braking system in a car, for instance. The system must ensure that the speed sensor and braking mechanism interact in real time to prevent V-lock. If synchronization fails, even a milliseconds delay could lead to a system failure endangering life. To avoid such delays, real-time operating system uses synchronization mechanisms like semaphore, mutex, and event flags to ensure tasks are executed in the correct order. However, real-time systems often face priority inversion, where a high priority task is delayed by a lower priority one holding a needed resources. This is solved with priority inheritance, which temporarily boosted the priority of the lower priority task so it can release the resource more quickly. This prevents system bottleneck and helps meet critical deadlines. Now let's talk about distributed real-time system, where tasks are executed across multiple nodes, sometimes across great distance. One example is fleet management system, where vehicles across the globe need to synchronize. A solution for this is GNSS based tick synchronization, which uses precise global timekeeping to ensure all nodes executed their task in sync, even if they are far apart. This level of synchronization is crucial for ensuring reliable performance across the entire system. Next, let's explore high performance computing HPC. HPC systems consist of thousands, sometimes millions of cores that works together to solve highly complex problems like climate modeling or molecular simulations. Synchronization in this system ensure that processes are executed in the right order without any race condition where threads could conflict and reduce and produce incorrect results. In the past course, grain locking was used to prevent race condition by looking large section of data or code. However, this often leads to contention where threads would compete for access to the same resource, slowing everything down. The solution to this is fine-grained synchronization, which look only the necessary portion of data, allowing multiple threads to work in parallel without interfering with each other. This technique is like allowing different people to use separate parts of library without locking the entire building. Another innovation in HPC is the use of atomic operation like compare and swap CAS. Atomic operation allow threads to update shared data in single, uninterruptible steps, avoiding the overhead of traditional locks. This reduces waiting time and improves overall system performance through it require careful implementation to avoid subtle bugs. HPC systems also rely on cache coherence protocols like MESI, which ensure that all cores have the same up-to-date view of shared data. Without proper synchronization, some cores might work with outdated data, leading to calculation error. Cache coherence is critical to ensuring data integrity in large-scale computing environment. Multiple cores operate in parallel. Moving on to the distributed system, where tasks are spread across many nodes, synchronization is essential for maintaining consistency across the network. Distributed systems face additional challenges like network latency and partitioning, where nodes may become temporarily disconnected from the network. Synchronization in this system is more complex due to these factors. To manage synchronization in distributed system, consensus algorithm like PECOX and REFT are used. This algorithm helps nodes agree on a shared state even if some nodes are delayed or disconnected. In distributed database, for example, consensus algorithm ensure that data remains consistent across different nodes even when changes are happening at the same time. Another technique used in distributed system is the vector log or logical timestamp, which helps order event across different nodes without requiring real-time synchronization. This mechanism track the sequence of event and allow nodes to apply updates in the correct order even if they happen asynchronously. This is especially useful when real-time synchronization isn't feasible due to network delay. Finally, let's discuss hybrid simulation platform, which combine software and hardware simulation to discuss system like system on chip (SoC). Synchronizing these components is crucial to ensure that the simulation reflects real-time interaction between hardware and software. If the hardware and software aren't properly aligned, the simulation could produce incorrect result, leading to design flaws. One solution in this area is synchronization profiler, which help developers synchronize the timing of hardware and software simulation. This allows them to spot bottlenecks and improve the overall efficiency of their designs. Maintaining tight synchronization between hardware and software model could ensure that the system meets performance and power consumption required, particularly in embedded system where these factors are critical. In conclusion, synchronization plays a crucial role in many areas of computing, from real-time system to distributed networks and high-performance computing. The research highlights the complexity of synchronization that the various solutions develop to make it more efficient and reliable. As computing systems become more sophisticated and interconnected, synchronization will remain an essential component, ensuring that the system can work together seamlessly. Thank you. Now my teammate Arushi will continue.
Today, I present an overview of synchronization in modern computing systems, drawing from key research papers. Synchronization is critical for managing how multiple threads or processes access shared resources like memory or data structures. It ensures system performance and prevents issues like race conditions, deadlocks, and performance bottlenecks. As its core, synchronization balances two key priorities: throughput and fairness. Throughput measures how efficiently a system completes tasks, focusing on speed, while fairness ensures equal access to resources, preventing any single thread from monopolizing them. In systems, prioritizing throughput like coarse grained locking, performance is high when contention is low, but it can cause delays and unequal resource distribution. In contrast, when fairness is prioritized, the system performance may decrease. But all processes can make equal progress, which is crucial in real time applications. Traditional synchronization mechanisms. Common mechanisms like mutex, spin locks, and semaphores are used to manage resource access in multi threaded systems. Mutex prevent multiple threads from accessing the same resource simultaneously, ensuring a safe access. Spin locks continuously check if a lock is available, which can waste CPU cycles if the threads wait too long. Semaphores control how many threads can access a resource concurrently. However, in modern multi-core systems, traditional methods like coarse grained locks, which lock the large section of a code, can often lead to performance bottleneck. When one thread holds a lock, the other thread must wait, wasting CPU time and reducing system parallelization. This significantly hampers the performance, especially in high contention environments. Now let's look at fine-grained locking. Fine-grained locking improves performance by locking smaller portion of code or data, allowing multiple threads to access different parts simultaneously. This increases system parallelization and enhancing throughput in applications like database, where thread can update separate rows concurrently. However, fine-grained locking is not without risks. Managing multiple small locks increases complexity and it can lead to deadlocks. When two or more threads wait indefinitely for each other to release their locks, or live locks, where threads continuously change states without making the progress. This makes fine-grained locking more challenging to manage in large-scale systems. Lock-free synchronization. An alternative approach is a lock-free or non-blocking synchronization. Algorithms like compare and swap or fetch and increment allow threads to access shared resources without waiting for locks. If a thread encounters contention, it retires the operation until successful, ensuring that at least one thread is always making a progress. Lock-free algorithms reduce the risk of deadlocks and improve the performance in high contention environments. However, these algorithms also rely heavily on hardware support for atomic operations, which are essential for their efficiency. If a system's hardware struggles with atomic operations, lock-free algorithms may not perform as well as traditional locking methods. Impact of hardware. Hardware architecture plays a significant role in synchronizing performance. In non-uniform memory access (NUMA) architectures, where the memory access times vary based on the core access the memory, synchronization can introduce bottlenecks. In this system, maintaining cache coherence or ensuring that all cores have the same view of data adds overhead, particularly when threads access the shared data across the devices. In uniform memory access UMA system, where all core access memory equally, synchronization is more predictable. However, cache contention, where multiple threads access the same cache line, can still degrade the performance, even in UMA systems. Managing message passing systems. An alternative to traditional shared memory synchronization is message passing, where processes communicate by sending messages rather than sharing memory. This eliminates the needs for lock and reduce cache coherence overhead, making it ideal for systems with high core counts and contention. However, in systems with low contention, traditional log-based system may still be more efficient due to its lower overhead. Synchronization in real-time systems. In real-time systems, synchronization becomes even more critical as tasks must meet strict deadlines. For example, in a robot operating system, synchronization can be a bottleneck. ROS lacks native real-time support, limiting its use in time-sensitive applications like autonomous driving. Synchronization, where threads waiting for a lock are suspended, improves CPU utilization, allowing the system to perform other tasks in the meantime. Additionally, gang scheduling, which ensures all threads of a parallel application run simultaneously, helps avoid synchronization delays, keeping all threads progressing together. Conclusion. In conclusion, synchronization is essential for modern computing, particularly in multi-core, distributed, and real-time systems. Traditional locking mechanisms like mutexes and semaphores struggle in highly parallel environments, leading to the adoption of fine-grained locking and lock-free algorithms. However, each synchronization mechanism has its trade-offs, whether in complexity performance or hardware dependence. As systems grow more complex, innovative and synchronization will be crucial to ensuring the efficient resource access, performance, and scalability. Thank you.
Now, uh, Now synchronization is a fundamental concept in modern computing, particularly in environments with multi-threaded applications, distributed systems, and multi-core processors. As systems grow more complex, ensuring that processes and threads access shared resources without conflicts becomes a major challenge. Synchronization is necessary to prevent issues such as race conditions, deadlocks, and performance degradation due to resource contention. Across the papers examined, various synchronization techniques and challenges are explored, focusing on log-based mechanisms, log-free algorithms, real-time constraints, distributed system consistency, and optimization for cache affinity and thread scheduling. Uh, at the heart of synchronization challenges is the need to manage access to shared resources such as memory or data structures in a way that allows multiple threads to operate concurrently without causing conflicts. Race conditions occur when two or more threads attempt to access and modify shared data simultaneously, potentially leading to unpredictable and incorrect outcomes. Deadlocks, another common problem, happen when uh, now traditional synchronization mechanisms such as mutexes, semaphores, and spin locks are widely used in multi-threaded systems to manage resource access. These mechanisms ensure that only one thread can access or modify shared data at a time, preventing race conditions and other errors. However, these lock-based methods introduce their own challenges, particularly in modern multi-core architectures. For instance, mutexes can lead to performance degradation when multiple threads are forced to wait for a lock to become available, reducing the system's parallelism and causing underutilization of CPU resources. One of the central issues discussed across the research is the trade-off between system throughput and fairness in synchronization mechanisms. Throughput refers to how efficiently the system handles tasks, while fairness ensures that all threads or processors have equitable access to resources, preventing starvation. In environments where high throughput is prioritized, such as in grained locking techniques, systems may perform well under low contention. Um, one potential solution to the limitations of coarse grained locking is fine grained locking, which provides more granular control over resource access. Fine grained locks protect similar sections of code or data structures, allowing multiple threads to access different parts of resource concurrently. For example, in a database system, the fine-grained locking enables different threads to update separate rows of a table without interfering with each other. Now, the increased number of locks can lead to new synchronization challenges such as deadlocks and live locks. Deadlocks occur when threads are blocked in a circular wait condition, each waiting for other to release a lock. Live locks, which are very less common, happen when threads continuously change states in response to each other without making progress. Now, another promising approach to addressing the limitations of lock-based synchronization is to use lock-free algorithms. Lock-free synchronization avoids the need for traditional locks by allowing threads to operate on shared data without blocking. Techniques like compare and swap, which is known as CAS, test and set, and fetch and increment enable threads to attempt operations on shared resources without waiting for a lock. Now, the performance of synchronization mechanisms is also influenced by the hardware architecture of the system. In non-uniform memory access, which is NUMA architecture, memory access times vary depending on which core or socket is accessing the data. Synchronization becomes more challenging in some systems because maintaining cache coherence, ensuring that all cores have a consistent view or shared memory, requires significant overhead. Now, a cache or coherence protocol such as MESI, which means modified, exclusive, shared, or invalid, are used to manage the consistency of shared data across caches, but these protocols can introduce performance penalties when contention for shared resources is high. As threads on different cores frequently access the same memory location, the overhead of maintaining cache coherence grows, leading to performance degradation. So, this was our conclusion of all these research papers that we have collected. Thank you.